Welcome to the Q versus K and common ion effect video. This video covers two separate but somewhat related topics. So by the end of this video, you should be able to use the ion product constant, or Q, to predict whether precipitation will occur. That's the first topic. And then the second major topic, the common ion effect, you should be able to understand what the common ion effect is and how it works, and you should be able to predict solubility changes in the presence of a common ion. So let's start with Q versus K. Recall from the equilibrium unit that Q can be used to determine whether a system is at equilibrium or not. Remember that if Q equals K, the system's at equilibrium. It also tells us if the system is not at equilibrium, which direction it needs to move to get to equilibrium. If Q is greater than K, then the system will move in the reverse direction to achieve equilibrium, and when Q is less than K, it will move in the forward direction to achieve equilibrium. We can apply those same concepts to a solubility equilibria. In this case, Q will tell us whether the solution is saturated or not. In other words, is it at equilibrium? And if not, can we dissolve more ions in solution? Is the solution unsaturated? Or are there too many ions dissolved in solution, and therefore a precipitate will need to form? So the ion product constant is basically just the Q value for the KSP expression. Recall that we determine the Q value by plugging given concentrations into the equilibrium expression. Basically, we're asking ourselves, are these concentrations equilibrium concentrations? And if not, what needs to happen to them to get them to equilibrium concentrations? In this case, our answer has a very specific meaning. So if Q is greater than K, that means that we have exceeded saturation. There are too many ions in solution. The system can't hold that many ions. How do ions remove themselves from solution? They form a solid and sink to the bottom. So precipitation will occur when Q is greater than K. When Q is less than K, that means our solution is unsaturated. You could potentially dissolve more ions in solution. The ion concentrations are not that of a saturated solution. Therefore, no precipitation will occur. And finally, if Q is equal to K, that means that the system is saturated or at equilibrium. So any more ions will cause a precipitate to form. Let's look at an example of this mathematically. Here we have a sample of lead 2 chloride being dissolved in hot water. Recall that salts tend to be more soluble at higher temperatures. Then we cool the solution to 25 degrees Celsius. Here's the KSP for lead chloride at 25 degrees Celsius. Will a precipitate form? So first we're going to start by writing the dissociation equation. So PbCl2 is going to be in equilibrium with Pb2 plus ions and 2 chloride ions. Then we'll write the equilibrium expression. In this case, KSP is going to be equal to the lead 2 plus concentration times the chloride concentration squared. Then we need to determine our ion concentrations. Let's take Pb2 plus first. Since we've dissolved 0.010 moles in 0.150 liters, we get a lead 2 plus concentration of 0.067 molar. Notice that for every lead 2 plus ion, we get 2 chloride ions. There are twice as many chloride ions in solution as there are lead ions. Therefore, our chloride concentration is going to be 2 times our Pb2 plus concentration, which is going to be 2 times 0.067, which gives us 0.13 molar chloride. Now that we have concentrations under these conditions, we can determine our Q value. So our Q expression is going to be the same as our K expression, so Pb2 plus concentration times Cl minus concentration squared. So in this case, 0.067 times 0.13 squared. Doing that math, we find that Q is 0.0012. Now let's compare Q to K. So our K value, recall, was up here in the problem. We can easily see that in this case, our Q value is much greater than our K value. That means these ion concentrations are too high. The system can't support that many ions in solution. Since Q is greater than K, a precipitate will occur. Ions will need to come out of solution in the form of a solid. Here's one to try on your own. Pause the video here, and when you come back, I'll reveal the answer. This one's slightly different because it doesn't involve a temperature change. Instead, it involves combining solutions with each of the constituent ions. So you'll need to start by determining your concentration of calcium ions and your concentration of sulfate ions in order to determine your Q value. Welcome back. Here's what you should have gotten. Notice first I calculated my calcium concentration and my sulfate concentration using the values given from the problem. Then I wrote my Q expression for the salt that I'm interested in, and I plugged in the values I calculated, determining that Q is less than K. Since Q is less than K, the solution is unsaturated and no precipitate will form. In other words, the ion concentrations are low enough that we could actually add more ions before reaching saturation. Now let's look at the other concept in this video, the common ion effect. The common ion effect tells us that the presence of a common ion will affect the salt solubility, and this is based on Le Chatelier's principle. Let's consider the dissolving of calcium fluoride, which is represented by the dissociation equation shown. When we add calcium fluoride to water, it dissociates into Ca2 plus ions and F minus ions in a 2-to-1 ratio since there's 2 fluorides for every 1 calcium. Now let's consider a scenario where I add calcium fluoride to a solution that already contains some fluoride ions. I'm just going to draw a few in here. In this case, thinking about Le Chatelier's principle, we already have some fluoride present. Therefore, our fluoride ion concentration will increase when we add the calcium fluoride. This will cause our equilibrium position to shift left to accommodate those extra fluoride ions. This means the calcium fluoride will be less soluble in a solution that already contains fluoride ions. Fewer calcium fluorides will be able to dissolve. In summary, a salt is less soluble in a solution that contains a common ion. Here's one for you to consider on your own. Pause the video here and try to determine which of the following solutions CaBr2 would be the least soluble in. When you come back, I'll reveal the answer. Welcome back. Here's what you should have determined. First, consider that NaCl will dissociate into Na plus and Cl minus, and NaBr into Na plus and Br minus. Since NaCl doesn't contain any ions that are in common with calcium bromide, we can eliminate A and C. Now comparing B and D, they both produce bromide ions, which is a common ion. However, D has a much higher concentration of bromide ions. Therefore, it will cause calcium bromide to be less soluble because there's more of that common ion. That brings us to the end of this video. Let's review our goals. First, we looked at how Q, or the ion product constant, can be used to predict whether precipitation will occur. If Q is equal to K, the solution is saturated. If Q is greater, precipitation will occur. And if Q is less than K, the solution is unsaturated and no precipitate will form. Then we looked at what the common ion effect is and how it works. Then we learned to predict solubility changes in the presence of a common ion. Generally speaking, the presence of a common ion will decrease the solubility of a salt.